Good morning, everyone. We are now getting ready for your own presentations, and so make sure that you watch the data talk. That will give you an example of how to do these presentations and even ideas for how you can talk about what your different elements are. Before we get to that, though, I promised you one last Q&A session. In this last Q&A session, we've had many of these, and I do want to go, we've now got the big picture kind of questions for these. So I want to do these, and I want to also, I'll be thinking about these questions and how they might be reflected on the test. You'll probably get questions that combine physical chemistry concepts with the big picture kind of things that you're asking here. So I'll try to drop a few hints along the way. So just make sure that you're going through everything that you know that's assigned, and then you'll be ready for the test on Thursday at 4 p.m. And the presentations before that, Tuesday at 4 p.m. Okay, so let's get to it. How did the rise of oxygen in Earth's atmosphere change the redox chemistry of metal ions? And the important thing about this is change the redox chemistry in a particular direction. That means that you are always going to be, you have more oxygen, you're always going to be moving in a more oxidized direction, which means that it's going to be taking electrons off, moving from the lower plus to the higher plus in general. But the thing is, that's not the only thing that's going on. In the oceans, you also have counter ions. So the question is not just what happens to the metal ions, it's what happens to the solubility. So KSPs become very important, and those might show up on the test. So you want to be sure that you review those kind of calculations, look at in your homework, know where those are in your homework, because you'll be able to access that and go back to that on the test. Okay, so your homework will be given that way, and it will be used in that way. So yes, the how they will move in general is more up in pluses, because they will have their electrons taken away by the oxidizing power of the more oxidizing atmosphere. That will also mean that they will bind to oxygen more. If there's more oxygen around, they could form the more oxidized form, like if you have phosphate or if you have borate or anything 8, you're going to be able to have more of the oxygen's form of that. Now there's a lot of things to consider, but the big thing to consider is KSP. So if you look at this, this is a good example. Iron changed from iron 2 to iron 3. It did not dissolve so well because of the counter ion when iron forms iron hydroxide, which has a very low KSP, very low solubility. Technically, that would be a, yeah, I think that would still be a low KSP. It depends on how you look at the number. Do the calculation to be sure. But the main thing is low solubility for iron hydroxide. And so you can look at the other things, and there's also possibly iron chloride. The question is how much of what is around. But you always have a significant amount of iron hydroxide, close to 10 to the minus 7th concentration. So from the concentration of the iron 3 and its counter ion, you can figure out what the solubility is. So this is why the whole first part of the book went through the whole idea that liquids were important. Liquids are important because to be in the liquid state, you have to be soluble. And not everything is soluble. If it's more stable in the solid state than the liquid state, then it's more like it's more in that way. There's actually a part of the lecture, and I forget exactly which chapter this was in, but it's toward the end of it. I think it's toward the end of the electrochemistry chapter, yes, because it's where we are talking about how you can add up the solvation energy of an ion. That's how its energy when surrounded by water, and compare that to the gas phase energy. Remember that there's a lot of other things around than just the metal ion. There's a lot of water, so there's solvation. There's counter ions, so there's solubility compared to the solid phase of the counter ion combined with the charged metal. Okay, go back and look at that part of the lecture in particular. I believe it's the end of the electrochemistry chapter. I think we might have been finishing things up, so it might not stand out to you, but that's about how to add up these different contributions. Well, we did it in the context of reconciling the calculations that we have with ionization energy, which is just taking off an electron, with redox chemistry, which is taking off an electron in water with other things around, you know? So that's actually related to this question right here. So the periodic table definitely constrained. Other factors such as gene mutation play an equally major role, and in fact, this is the whole point of Chapter 12. Chapter 12 is talking about different levels at which we have different things that are constrained, different things that happen according to different kinds of laws even. And so what does it mean? It's important to realize that there can be chemical laws that constrain what can happen. Then you can have like biological laws that are related to the chemistry but cannot be reduced to the chemistry. There's some irreducible novelty, if you remember that term, that happens when we have a biological law like gene mutation law going on. And the level of the mutations and gene mutations can change once you have that set up. They can change to any gene mutation they need, but it needs to provide a function. Function is important in the context of the organism and its ecosystem. So yes, this gets far beyond chemistry, but I want to say that chemistry is about the periodic table, and life is built on the periodic table, so in some ways it's constrained. In some ways, life has a certain freedom with the gene mutation that it has, and organisms can even rewrite their own genomes. So realize this gets really fascinating. It seems like, we have these boxes, physics and then chemistry and then biology stacked on top of it. And that's true from a bottom-up way of looking at it. You can also have a top-down way of looking at it where you have biology has a need to live and to have homeostasis, which is keeping life the same, which fights against the chemistry law, second law of thermodynamics. So you can actually have conflicts between these. And the thing that's interesting is it looks like within this context, life wins. Within the context of the biosphere of life on Earth, the biological law of survival and thriving, what's the word I'm looking for? It's like living, homeostasis. The law of homeostasis actually beats the law of chemistry, although you can't go outside the law of chemistry, but it beats the law of chemistry that is thermodynamics. You can't go outside the laws of solubility. So there's a complex interplay of what you can do and what you can't. But just remember, this is really fascinating. In Chapter 12, it's where it really opens up. And in a sense, I feel like the irreducible novelty paper that I had you read for capstone, that actually is involved with other things like the questions like this. And so it's fascinating to think about that, but this class focuses on how do chemical laws make a box that life has to live in and in a sense fight against. Life often wins. Life finds a way, right? That's the quote. So the lifelong complexity is somewhat inevitable, and this is why in Chapter 4 we talked about different planets. Different Earth-like planets likely have similar biology to us. The one thing I would add to this, Earth-like means water-containing, oceans of water. So that is already a chemical box that you have to fit in. Is there something other than water that would work? Formaldehyde, maybe, but I'm not convinced that formaldehyde is available in oceans anywhere. And also it has certain reactivity patterns that are different than water. And so it might provide a liquid phase, but it's probably not the right blend of being reactive and non-reactive. But we can argue about that. Basically, the Chapter 12 is saying we can argue about this. That's the whole point of Chapter 12. And we're going to find more Earth-like planets, and the question is, are they water-rich, is in the first thing. The other place, I say you have to have liquid. And chemically having liquid under normal, like Earth-like temperatures and pressures, I wonder if water is really the only way to have oceans of liquid phase open to the other phases of life, both gas and solid. That's the argument. But that's what I want you to think about. I don't really know. Both of these questions are open questions. The other thing that I want to think about is, what about sun? We've talked about the electronic transitions in physical chemistry and how those are not really open for, electronic transitions are not open for life to use that much. In a limited way, it's what we're talking about when we talk about redox chemistry, but even that, only a few happen and only in certain ways. Well, what if you're in the heart of the sun, where electronic transitions are a lot more available, and other kinds of bonding are not available. So you have to provide structure, and you have to be able to actually, you have to provide structure on the one hand, but dynamism on the other hand. You have to be able to hold something in place. You also have to be able to move. Maybe there's a way in the heart of the sun where you have plasma rather than liquid, and you have electronic transitions rather than rotational vibrational. Maybe you can set up, but I don't know if you have enough diversity, chemical diversity, to be able to set up structures that would be the equivalent of the complexity of proteins, membranes, and life itself. So I would say two things. Formaldehyde, maybe, or maybe if you can find something else like formaldehyde, but it needs to be there in an ocean, needs to be liquid, needs to be open to the other two phases. Or maybe the plasma phase and electronic transitions. You've got to talk about what energies are available. If you want to talk about this fantastic thing that could happen, but you need like basically infinite energy to do it, well, we don't have infinite energy. We have to work under these constraints. Part of the lesson of the book is that these are the chemical constraints that life has to operate under. And I want you to think about that, because the calculations you're doing in the homework are all about the chemical constraints life operates within. And that's why you can probably have some of this on the test. I put this as the last question because it really does open up into history. We don't talk much about human history because it doesn't exist in the story until chapter 11. But in that, it does kind of fascinate me. So how do I see physical chemistry offering more insight into the human experience? Well, it's through the human experience, which is qualitative, not quantitative. It's psychological and even spiritual. And so the thing is, it opens up to the things of mind and life, and actually it opens up to top-down kind of processes rather than bottom-up processes. And I am still thinking about how this question works, but one of the ways I've answered it is to talk about the human experience of art and perceiving color, and making colors, and then putting those down into art. I actually have a book mostly written, I hope to finish it this summer, that's going to be about this whole idea of how does chemistry give us colors, how did we use those as artists, how they open up new colors for artists to make new art. So that's one way, through colors. There's other ways through energy, there's other ways through anything that chemistry affects. You can kind of think about energy moving. Basically, if you can make something or you can move something deliberately, then human agency takes over. And this is fun. I don't want you to, there's a lot of voices saying that you're just a machine, you're just a mindless computer. You know, now we have these computers and they're going to take over for us because they're better at their thinking than we are. For certain tasks, that might be partly true, but for most important tasks, the most important tasks, it's not true at all. Your experience, even seeing a color, is something that a computer can't really do. So you have something with your human experience, and this is why I want to leave you on. With your human experience, you have something special that's a gift to you. And we have a history of people using those gifts, again, as constrained by chemical laws. And that means that certain colors even are named in a certain sequence. Every culture names red first. Every culture names yellow second. It's not quite that tight, but it's pretty close to being that tight. It's a surprisingly good sequence that most cultures will not separate green from blue. This is naming things until later in history. This is naming colors that are perceived by humans. This is not a mechanical thing. This is a soul thing, a spiritual thing. And so this is where physical chemistry can offer insights, but also human experience has to offer insights to the physical chemistry, how it's used. It always must be a tool and not the main event. The main event is the education of the soul. That's why I want you to work at these things. I want you to think about these things, ask these questions, do these homework problems to use math as a tool for answering these exact questions. So that's how physical chemistry is also about the atoms, and that's about the bottom-up processes. There are also top-down processes, and it's the top-down ones that are more important. And ultimately, I'm convinced the top-down ones win. Mind, life, and language are these top-down things, and these are things that involve the soul and not the body. Well, they involve the body because the soul incorporates the body. Anyways, you got to be careful how you talk about all these things, but I want you to open that door to put chemistry in its proper context. It has a lot of power, but it also has limits, and imposes limits on other things, but they also have a lot of power. Okay, so that leads me to say, I want you to tell me about the power of chemistry, what the laws of chemistry say, the physical chemistry say about how these things are limited. Maybe you can address one of these questions in your own talk. And so iron, calcium, and magnesium are what we will talk about Tuesday at 4 p.m. in our usual classroom. So I hope to see you then. I hope to see you then. I need to see you then. Okay? All right. Thank you for a good year of physical chemistry. Thank you for taking this in, and I look forward to seeing what you will do with this.